Okay, everyone, so I want to go ahead and talk to you about these worksheets first, and then, of course, go through this first worksheet with you. So the worksheets were made actually last semester, last spring. Of course, there's a pandemic-ridden spring, and so we were trying to do hybrid-type classes. And so the class was listening to the lectures that you're actually listening to in Echo 360, and and then they were doing in-class work. We'd bring them together in small groups and do in-class worksheets. Okay, and there was a lot of positive feedbacks with the worksheet, and I think that are very helpful in terms of preparing students to do well in the class. So I wanted to go ahead and make these available to you, but not have synchronous meetings, because I know that synchronous meetings sometimes can be difficult for online students. And so we're not going to do it synchronously, but I do want to make available to you, first of all, the worksheet so that you can do them, and then secondly, the feedback that I would give you if you were in a synchronous session. All right. Now, my suggestion with these is to go ahead and, first of all, just do the worksheet, okay? And you might feel a little bit strange. You might feel like, oh, man, I don't know this. And that's okay. That's part of the discovery process. It's part of the learning process. It's okay. These are low stakes. In fact, there's no stakes on these, right? You're not getting grades for these. They're optional. But go ahead and do them, and then that way you've kind of thought through them, and then get my feedback, and that will hopefully help you correct yourself and make course corrections as we go through the content in the class, and hopefully that will help you perform better on some of those quizzes, as well as, of course, the exam, which are high stakes types of assessments. Okay? All right, so let's go ahead and look at this first worksheet, and this is going over material essentially in that lecture 1, that laying the foundations, and there's lots of stuff in that, of course, but we're not going to go through all that in this worksheet, but there is some very important couple of concepts that I think that we want to think about that will have that if you understand will have real benefit for you as we go through the rest of the semester, and that is going to be this idea of a steady state and how that's connected to the flux of different pathways. Okay, so in the beginning of this worksheet, it describes a steady state. Right now, right, you're at rest, your skeletal muscles are at rest, but there's lots of other processes going on in your body. For instance, you're breathing, obviously, your heart is beating, there's lots of activity going on in your other organs, okay? And all those activities take ATP. There's literally millions and millions of molecules that are of ATP that are being used on a second by second basis in the cells in your body, and yet, despite all that usage of ATP, that ATP, the levels of ATP, the amount of ATP that's in those cells stays fairly constant, okay? It does fluctuate, it goes up and down a little bit, of course, but it goes up and down within ranges. It never gets too low, it doesn't ever get really too high. And the reason that is the case is because your body, okay, and the cells within your body has the capacity to regulate the flux through pathways that are using ATP and that are producing ATP. Okay, and therefore they can balance or keep in a steady state, if you will, or homeostasis, the amount of ATP found in those cells. Okay, and so we want to go ahead and talk about that in this this lecture. Okay, now something to think about with the steady state is that it's not it's not an equilibrium state. Okay, it's a far from equilibrium state, actually. Okay, if you were to allow ATP concentrations to reach equilibrium in the cell, there would be no ATP left, okay, because ATP will be broken down almost entirely to ADP and inorganic phosphate at equilibrium. Okay, so keep that in mind as well, right? So let's go ahead and look at this. And the first thing that we want to do is I call it activity 1, okay, and we want to look at how a pathway is designed so that we can then talk about how its flux can be regulated in order to maintain steady states, okay? And we're looking at, of course, a hypothetical pathway. Now, if you haven't done activity 1, go ahead and pause it and do it now, okay? This will be a good time to do that. Okay, if you have, then let's go ahead and give you that feedback. And the very first thing that's asked of you in activity 1 is to assign C values, okay? And these will be control coefficient values for this hypothetical pathway. And all the information that you're given is essentially what you're seeing on the screen right now, okay? And something that we want to recognize about metabolic pathways is that they are designed to have two different types of reactions within them. They have these reversible steps. Okay, right here would be an example of a reversible step. There are the equilibrium arrows. And then they have these irreversible steps that are represented by these single-headed arrows. Okay, and all metabolic pathways, or most metabolic pathways, I guess I should say, have reversible and irreversible steps. Okay, the majority of steps within a pathway are reversible. Okay, and those reversible steps are catalyzed by enzymes that are very efficient, or there's a lot of the enzyme, or both, and because of that, then that step is usually at equilibrium. Okay, and it will respond in terms of its rate to essentially Le Chatelier's principle. Okay, meaning this, like if you were to take this first one, okay, A goes to B. If A concentrations all of a sudden go up, then that's going to increase the rate of the production of B. Okay. However, we could also see a scenario where B concentrations go up, and that will increase the rate of the production of A. Okay, that's a reversible step. It can go in either direction, and the rate at which it's going to produce A or B, okay, is based off of the pressures that are put on that. Okay, according to Le Chatelier's principle. Okay. Now compare that then to these irreversible steps, the ones indicated by these single-headed arrows, and there's two of those. Okay, these are catalyzed by enzymes that are actually purposely inefficient. Okay, the cell is usually keeping their rate fairly low. There may be inefficient enzymes, maybe they're being negatively modulated. Okay, there's some sort of regulation on them that's slowing them down. Those become our rate limiting steps. Okay, in fact, I could put here rate limiting steps of this pathway are these two irreversible steps. Okay, and that's where regulation of the pathway is going to occur. Right now, when we then think about this in terms of these flux control coefficients, okay, we assign C values that are fairly high to the rate limiting steps and virtually 0 for the non-rate limiting steps, those reversible ones. Okay, so we would want to put C values over these guys. Okay, and it says assume that they have equal contribution, that both of those steps have equal contribution to the flux of the pathway. So what I'm going to do is I'm going to assign a C value of 0.5 to this one, and I'm going to assign a C value equal to 0.5 for this one. Okay, and then the C values of everything else, I won't write this out, but the C values of everything else would be 0. Okay, a C value of 0 means that there is no contribution to controlling the flux through this pathway by that particular step. Okay, whereas the C values for these two steps happen to be the ones that we're talking about, rate limiting steps, happen to be quite high. Okay, and what we would say here is that, okay, both of those steps have an equal contribution to regulating or controlling the flux through the pathway. Okay, now you might ask yourself, well, gosh, how would I know what value to use? Maybe I can identify what the rate limiting step, but how would I know what C value to use? Well, you wouldn't. You'd have to experimentally determine that. Okay, you could guess it here because I said there'd be equal contribution and by the two steps, and C values always have to add up to 1, and so we can say, well, 1 obviously divided by 2 is going to be 0.5. Okay, so that's the only reason that we get to 0.5. Now, in reality, that's not always the case. Okay, there are some steps that are more important than others in regulating the pathway. So, for instance, we could have the first step be a C value of 0.8, and the other one be 0.2. Okay, but they're always add up to 1. Okay, so that's just something to keep in mind as we go through this. Okay, so that's step 1 of activity 1. Okay, now you might say, okay, I think I've got it. Maybe I understand that. Okay, but what does that all mean? Okay, and that's where this next part I think is important. Okay, because we want to have some illustration of what this is. Okay, and so it says now represent the above pathway as an interstate, changing the number of lanes based on the assigned C values. Okay, an interstate meaning driving, right? When you get in a car and you get on an interstate and you have, right, a certain number of lanes that are accessible to you, and that's going to determine the rate at which traffic flows. Okay, and we know that when we're driving down an interstate, that there are times where the number of lanes change. okay? They go down or they go up, and depending on the volume of traffic, that can really screw us up, okay? Sometimes there's an accident and it gets all the way down to 1 lane, or sometimes there's a construction zone and it gets down to just 2 lanes with no shoulders, right? There's lots of things that go on. And so the same thing can be said and thought of with these metabolic pathways, that there are bottlenecks within metabolic pathways that are regulating or controlling how fast or the flux through that particular pathway. Those bottlenecks are, of course, your rate limiting steps. Okay, so if I were to then draw this metabolic pathway as an interstate, I would do it something like this. Okay, I'm going to go like this, and then we get the C goes to D. I'm going to go like that, and then come back up, and then I'm going to get the H goes to I. I'm going to go like that. I'm going to do the same thing for this. Here we are. Okay, so what I'm representing here is this. These would be the rate limiting steps, okay, within our metabolic pathway. You can very easily see that, oh, we have these bottlenecks, and these bottlenecks are these reactions that have these large C values, okay? And you can imagine then that those bottlenecks can get even tighter or thinner, right? And then that's going to cause even less flow of material through them, and that's going to slow the flux through the pathway. Or they can get wider, and if they get wider, then that's going to allow more material through, and then the rate of the flux through the pathway is going to go up. Just like we would think about with an interstate, right? How many times have you sat in traffic and thought, man, I wish there was like 5 more lanes right now. If there's 5 more lanes, then I'd be moving at a really fast rate, okay? And that's what you would want to see, okay? And so the same thing can happen within a metabolic pathway, sort of, okay? But I think this is a nice visual way to understand these C values and understand the design of these metabolic pathways, okay? Now, understand something, hopefully you're understanding this, but these, other steps, these reversible steps for rate limiting steps, these are represented by the wide sections within our pathway, right? So that's, I think, hopefully a helpful diagram to you, okay? Now, on to activity 2. Now, if you haven't done activity 2, then pause, right? And then come back and listen to the feedback. But if you have, then let's go ahead and move on here and think about this. So it says, let's move on into analysis of control for this pathway. Below is a velocity saturation graph, and let me get to that. This is what you're looking at. Is a velocity saturation graph of one of the enzymes in the pathway. Note the x-axis is the enzyme substrate C from the hypothetical pathway above. So this data represents this step right here. Let me get a nice color here, orange. This step here is represented in the data that we see here. Okay, C being the substrate of that, right? C. Okay, all right. So using this graph, redraw your highway during strenuous exercise in the skeletal muscle. Assume this pathway is found in the skeletal muscle. So let's go ahead and stop right there. Okay, and let's think to ourselves here. Let's go up here and look at our pathway and say, okay, we've got this step. C goes to D. That is regulated. It's one that has a C value of 0.5. Okay, we noticed that the very last step in the pathway, this one here, okay, is going to make ATP. And what we're saying here is that this pathway is found in skeletal muscle, and all of a sudden a person starts to undergo strenuous exercise. Okay, so they go from rest to very active muscle cells. Okay, those muscle cells, of course, to contract are going to require lots of ATP to do that. Okay, and so ATP levels are going to all of a sudden plummet within these cells. Okay, now let's go ahead and look at this. Okay, and let's just say that I'm going to go ahead and just use a black line here. Let's just say that the concentration of C within the cell is right where I just drew that little line here. Okay, so this is concentration of C in the cell. And it would be at a steady state concentration, right? Okay, and so what we want to do is this. We'll just draw a line straight up from this, okay? And at rest, when levels of ATP would be high, we would say that the rate of this enzyme, or the percent of its activity, is going to be somewhere around there. It looks to be about, 20% of its total activity. Okay. However, if a person was to start to exercise, what's going to happen to the ATP? What's going to drop? Of course, naturally, it's going to drop. That what we say, to get contraction going, the ATP levels are going to drop, and so all of a sudden, the ATP levels in the cell are going to go to low. Well, ATP must be acting as some negative modulator of this enzyme, so that when it's high, it's negatively modulated and it rates low, and so that when ATP levels drop, that we lose that negative modulation, and all of a sudden the rate of the enzyme increases to this. Okay. So in other words, we go from a situation where there's a fairly low rate of the enzyme to a fairly high rate. We could say that this is 85%. There's this almost 65% increase in the rate of the enzyme, okay? Because ATP levels have gone way down, okay? Now, what is that going to do to our highway? Well, let's come back up here and let's go ahead and draw this. Well, our highway is going to do this. I'm going to remove this. Okay, there we go. So I can draw this, and we'll draw the new highway, and it's going to be something like this. Okay, and we'll draw another one here, a little bump there. We got more lanes all of a sudden, right? Okay, so we've got more lanes. This, right? We had it here, and now we've got it here. That increase, okay, in terms of that bottleneck is due to this change here in activity of the enzyme. Now, in the Laying the Foundations lecture, we talked about how enzymes can be regulated, and one of those was through allosteric means. This ATP is an allosteric negative modulator of this enzyme, okay, and when it's gone, then we lose the negative modulator and we increase the rate of our enzyme, and therefore we get this, right, more lanes, more material can start to move through the top half of this pathway, okay? All right. Now, the next question says this: now that you have done this, let's see if we can't do some problem solving. First, is the pathway, given these conditions, going to produce more ATP? Okay, well, let's look at this. Is it going to produce more ATP? Well, it's tempting to say that it will, and I think that it probably will, though it probably won't produce as much as we would like it to produce. Okay, and the reason is because we've still got this bottleneck here that has been unaffected by what's going on up there. Okay, in other words, that ATP levels affected a portion of the pathway that controls flux, but not the other portion of the pathway that controls flux. So while we get more material through this top half up here, we're not getting as much material in this bottom half. Well, notice up here, right, this bottom half is right here. Okay, and that's what's producing the ATP. So, and there's a bottleneck right before we start to produce ATP. So that bottleneck has to be dealt with before we can see massive increases in ATP production. And of course, the cell needs to do that, especially if it's undergoing strenuous exercise. So it says this: what could be done in order to produce more? Be specific. By this, I mean propose a mechanism for doing so. In your proposal, keep in mind the needs of the cell and the time scale in which those needs must be met, okay? Right? So this is a reference to the types of regulation that we can see within enzymes, okay? So one of those types of regulations could be to increase the genetic expression of this enzyme that catalyzes this step here, the H to I step, okay? You know, I don't know what the name of the enzyme is, whatever it is, okay? But you could increase genetic expression of that, but that's slow. Right, that's not gonna meet the needs of the cell, right? So, for instance, if you take off on a sprint, okay, imagine an Olympic sprinter, they need ATP right away, right? So they don't want to. Their cells can't wait around for increased genetic expression of that enzyme. They need to have some rapid change in regulation. Okay, so what are other ways to do this? Well, let me say this. This is a really interesting one. Right, down here, or up here, I guess we could say, we're going to all of a sudden start producing a lot more D, right? Because ATP concentrations went down, so D concentrations are going to go up because we're getting more material through this step. Well, what if D was a positive modulator of that enzyme in what would be considered a feed-forward mechanism? In other words, D is an allosteric positive modulator of that particular enzyme. So you can imagine this, right? We could say that, come back to this graph, we could say that this graph would represent now concentration of, I think it's I, right? That's, or no, it's H probably. Yeah, H. Okay, erase that. There we go. Concentration of H. Okay, instead of concentration of C. And then we say, okay, this would be, get rid of this. This would be a scenario when we had high concentration of D, the metabolite D, and this could be, right, the scenario in which there's a low concentration of D. Okay, so in this case now, we're saying that D concentrations are low, the rate of that particular enzyme that converts H to I is going to be slow. Okay, but when concentrations of D go up, all of a sudden we're going to see this huge increase, and that's going to then widen this gap up here. Okay, and notice that the widening of this gap here is dependent upon the widening of this gap there. Okay, because D won't be produced until ATP concentrations go down, and then once D is produced in large amounts, it can feed forward and widen that gap, and then you're going to get more ATP. So that's one mechanism. Now, some of you might have said, well, couldn't there be like covalent modification of that enzyme? Sure, there could be. For instance, you could see that the increase in D could activate a kinase that would then covalently modify the enzyme that we're talking about here, or something else. I mean, there's lots of different ways to do this. Or ATP or ADP could do this as well, right? ADP, the breakdown product of ATP, could be a positive regulator of that particular step, right? So there's lots of different mechanisms. I don't want to say there's only one right way to do this, but there is ways to think about this, and feed-forward mechanisms are fairly common. So, okay, that's it for this first worksheet. I hope that you find these helpful. We'll do these periodically throughout the semester. Okay, some of the worksheets there might be a little bit strange in terms of what they look like because they were designed for a face-to-face class, but we'll still work through them, I think, in an online environment. Okay, and hopefully you find them helpful.